So, as I said, I want to have an idea of the type of solutions of x dot equal to f of x without solving this equation. So the first thing I want to find out is equilibrium points. Okay, so an equilibrium point is a value of the state that if you start there, you stay there. It's constant in time. So how can I find equilibrium points?
Points where the derivative is 0.
So x dot is equal to 0 because if the derivative is 0, x is constant. No, x is constant. Now, if f x dot equal to 0, then I can find an equation on x that gives me the equilibrium point. What is this equation? If x dot is 0, then
Fx is 0.
f of x is 0. Okay? Example. Suppose that f of x is x is a scalar, and we have x m minus x. So you have an equilibrium at x equal to 0 and an equilibrium at x equal to m. We have studied this equation. It's the logistic equation. So I put a bar here to say that this refers to an equilibrium state. So I have my state space. Let's think it is a plane. So this is x1, this is x2, and I have here some x bar for which f of x bar is 0. Now, suppose that your state is not exactly at equilibrium, but it's here. So this is your x. So you have an increment that I call delta x. So this means that x is equal to x bar plus delta x. Okay? And I would like to find, so my problem is find an equation for delta x. So I want to say delta x dot, the derivative is something. What something? Okay? So let's pick up the original equation. So you know that I repeat it here. X dot equals to f of x. And now what shall I do? I want to find an equation for delta x. Suggestions.
We can compute the derivative of the equation that is written in green.
Okay, so maybe I could use this equation in green. I could find out the derivative, and the derivative of x is the derivative of x plus, which is of x bar, which is x bar is constant.
Yeah, it's 0.
0
Yeah.
plus the derivative of delta x. But this is just part of the story because you don't involve the f. So what could we do? Maybe considering this equation in green is important, but it's not the whole story because it does not involve f. So another idea. What about using the equation in green together with something else?
So the derivative of x, so x dot is equal to fx. And
so
if we
x
say
naught
x
is,
dot in that,
so
in
this
that
is the derivative on the left, the derivative of x bar plus delta x. And we know that this is what?
it is equal to f computed at x bar plus delta x.
Good. Do you agree, Kaveh?
Yeah.
Okay.
But
And now, yes,
okay, so you put like a x bar plus delta x
that's right.
instead of instead of x itself in a an equation.
So I know that x is the equilibrium plus the deviation from the equilibrium. This is
Okay.
exact. So up to
Okay.
now, no approximations.
Okay. Okay. Now
Now, what can I want to simplify things. Maybe this is not so. Actually, this is an equation on delta x, but maybe we can simplify things. I would like to have a linear equation for delta x. If delta x is small, maybe I can find a linear model for delta x. So what can I do? On the left, how can I simplify this expression for the derivative? We have just seen.
We just say it's the
it is okay.
derivative of x bar plus
That's
the
right.
delta
So
x.
this is the derivative of delta x. This is delta x. Delta t, because the derivative of x bar is 0. And okay, this is f of x bar plus delta x. Now, what can I do to make some approximation here?
Taylor expansion.
Taylor expansion in terms of delta x. So what is the Taylor expansion in terms of delta x?
It's f.
Okay, tell me.
I'm not sure, but I think it's f computed at x bar.
F at x bar.
Then we sum the derivative of
plus the derivative of what?
f.
Partial derivative of f with respect to
X.
X.
Computed
at
delta x.
X equal to x, not delta, x bar times delta x. Okay, and then plus other terms. Okay, so this is just the first two terms. This is very simple. Let me make a plot. Suppose, good Lord. So this is x, this is f of x. And you have some function here. Okay? Now, you have one point of this function, say x bar. Okay? Now, how can we approximate this? We take this point here and we draw a tangent line. Okay, so let's say at this point, x bar plus delta x. So if this is delta x, what do you have? The approximation is this point here. What is this point here? Is this point, which is f of x bar, plus what? Plus this increment. And this increment is what? Is the slope of this line, which is a derivative, multiplied by delta x, which is that term. Okay? Any question?
The last part, would you repeat it again? So you multiply the x bar.
I multiply. Let me pick up this. So to find this bit here, just this bit.
Okay.
Okay. This is what is the slope.
Okay.
Times.
Yeah. Times the
increment.
Yeah. Okay.
And so the slope is the slope is the derivative.
Yeah.
Compute it at this point.
Okay. Got it. Now.
So you don't compute the derivative at that delta x. You compute it at x bar.
Okay.
Is it okay?
Yeah. Now I understand. Yeah.
Max, you understand why this is x equal to x bar times delta x and not the opposite? Mm-hmm. Okay. So on the left we have the derivative of delta x. On the right we have the first order expansion. Now, can we make simplifications here? What can we simplify here? We have the derivative, okay. Then we have this term f of x bar. This is a vector of constants. What can we say about it?
It's zero.
This is zero. Yeah. Good, zero. No, by definition of equilibrium point. So what you have? You end up with, this is a matrix. Okay. And the derivative of delta x is a matrix times delta x. Okay. If you call this A, you have delta x dot equals to A delta x, which is a linear model. So everything that you should know, but you don't know about eigenvalues and eigenvectors in that story of the phase portrait applies locally, okay, locally around here, around the equilibrium, because it's when this approximation is valid to this system. Okay, so that's linearization. Now, we can, for instance, pick up a nonlinear system of equations, x dot equal to f of x. What we do, we linearize, we find the equilibrium points, and we want to study the behavior around one equilibrium point. We linearize, and we end up with a system of equations, of linearized equations for the equilibrium point. And then we study this. We can compute the eigenvalues and see whether it oscillates, does not oscillate, and so on. Okay. Now, if you have other equilibrium points, you do the same with a different A, because the x bar will be different. So this matrix of derivatives will be made of different numbers. This is not a function. This is a matrix of numbers. Okay, let's see one example. Now I go to the slides. Before I exit this page, do you want to ask something?
No.
No.
Okay, so let's go to the, so stop sharing. And I need my slides. Where do I have my slides? This is what? This is slide numbers, set file number 3. Okay. So I'm not going to show you all the slides. Just a few. And above all, I want to do an example with you. So this is the file number 3, MESCB 3. And if you look at it, you find exactly what I was mentioning. Okay, some remarks. Let's jump these remarks, all these remarks. Let's go to an example. And the example is this one. Suppose that you have these two equations, okay, nonlinear equations. You have two equilibrium points, you see. How can you find these equilibrium points? Just equate the derivatives to 0. So one of the conditions is what from the first equation?
X1 equal to x2.
X1 equal to x2. So you go to the second equation, which is 1 minus x1, x2 equal to 0. And you replace, say, x2 by x1. So you have 1 by x1 squared equal to 0. So x1 is either minus 1 or plus 1. Okay? So you have 2 points. One point is minus 1, and the other is 1, 1. If you want to have a geometrical interpretation, the first equation is a straight line, x1 equal to x2, so it's this straight line. And the other is x1, x2 equal to 1, which is an hyperbole. You have these two branches of the hyperbole. And at the points of intersection, both derivatives equate to 0, which is 1, 1, and minus 1, minus 1. Okay. Now, let's differentiate this. Let's differentiate this and compute the derivatives. So the matrix of first derivatives is the f1 dx1, the f1 dx2, the f2 dx1, and the f2 dx2. This is called the Jacobian matrix, from the name of the famous mathematician of the 19th century called Jacobi. Jacobi with a G, with a J. Now, f1 is x1 minus x2. So the f1, the x1, this is a partial derivative. Okay, this is just 1 because the derivative of x2 with respect to x1, partial derivative, you assume that x2 is a constant when you are considering the derivative with respect to x1. So this is just 1. Then the f1 dx2 is just minus 1 because the first one is 0. Now the f2 dx1 is what? Okay, the derivative of 1 is 0, and then you have minus, and it's the derivative of f2 with respect to x1. So when you differentiate with respect to x1, you get the other coefficient, which is minus x2. And the f2, the x2, you take x2 as variable, so the coefficient is minus x1. Okay? You should know how to compute derivatives of a polynomial or a linear function. Okay. Now, this is the general matrix of derivatives. It's a function. Okay, this Jacobian matrix is a function, but now you want to compute this at the both equilibrium. You have two equilibria. So you have one point which is -1, -1. So you go there and you replace x1 by -1 and x2 by -1, and you get this matrix of numbers. Okay, so this is the A matrix in turn of the point -1, -1. If you go to the point 1, 1, you replace x1 and x2 by 1, and you get a different matrix with different eigenvalues. Now, you could compute the eigenvalues and the eigenvectors, and perhaps...
So, sorry, I have one question. So the numbers -1 in at the first one and the second one, which is 1, so we give this value by ourselves, no, or we will find it in the equations before, because the value is like the x1 multiply x2 is equal to 1. So would you explain this part again? So how did you get this? Yeah.
You mean the equilibrium points?
Yeah, this one, yeah.
Okay.
So in this one, the x1 is it is like a -1, yes?
These are the equations. Now,
okay.
The conditions are x1 minus x2 equal to 0.
Okay.
Okay.
So
now, this condition defines a line, x1 equal to x2.
Yes, yeah.
Okay. So you have the line here, the straight line.
Okay. Yeah.
Okay. Now, this other condition means that x1, x2 is equal to 1. Okay. And x1, x2 equal to 1, it's a parabola, it's an hyperbole. It's this type of curve.
Yeah.
Okay. And you have two branches. You have this part here and you have that part over there.
Okay.
Okay. It's a conic curve. It's one of the so-called conic curves.
Okay. Now I got it.
Okay. Now, the intersection of two give you the equilibrium points, because these knots, for these knots, both derivatives are simultaneously 0.
Okay. Now I got
it. Okay.
Thank you.
Along the straight line, the first derivative is 0. So along the first line, you can even say that since the derivative of x1 is 0, you cross this line in the vertical.
Oh, yeah.
Instead, along the parabola, the second derivative is 0. So you cross the parabola in the horizontal. So you can use this to have an idea of the sketch. Okay. But I'm not going to make this example furthermore. So I've cut it a lot of slides. Now let's go to here. Remember this diagram? Depending on the eigenvalues, I know what is the type of solution in the plane x1, x2, so the phase portrait. Okay, so I can do a local analysis around each of the equilibrium point and find out what is the type of solution that I have. Okay, now the only problem is when I get pure imaginary eigenvalues, because the linearized system, in this case, are closed curves, and the nonlinear system may not be closed curves. It can be either stable or unstable. Okay, let me give you one example. This is one example. You have these two nonlinear systems, you see this one is turning around to the outside, no? It's getting bigger and bigger and bigger. And this is reducing. So the one on the left is unstable, and the one on the right is asymptotically stable. Okay. If you do the linearization is the same for both. And it has, if you compute the eigenvalues, you find two imaginary, pure imaginary eigenvalues corresponding to closed curves, you see? So when you have a linearization with closed curves, you can't take any conclusion about stability of the point. But if you linearize and all the eigenvalues have negative real part, you can say the nonlinear system is unstable, is stable, asymptotically stable. If at least one eigenvalue is positive, you can say it's the equilibrium point of this nonlinear system is unstable. Okay? Do you know? I'm not sure whether you was the first one to find this relation, but at least you used it. It was the first person to use this type of relation, this type of technique. So linearize the equilibrium points and study the eigenvalues of the linearized points to see the stability, to infer the stability of the nonlinear system. Do you know who was the guy? Was Maxwell. What does the name Maxwell tells to you? The laws of electromagnetics. Okay, he was a Scot. He was from Scotland. He was a physics and mathematician, more physicist than mathematician. And he wrote a very nice paper that you can find easily on the net. It's called On Governors, in which he analyzed the stability of the velocity of a steam engine, a steam machine.
Oh, yeah.
Okay. When you have this, you see these balls that turn, the faster they turn, so the farther away the balls go. So you have a lever, and you adjust the steam to regulate the velocity. Okay, that's the so-called Watt regulator. Okay, was invented in the end of the 18th century by James Watt. The problem was that sometimes this was becoming unstable. Okay, so the Royal Society offered a prize for the solution of the stability problem. And this prize was won by a paper of James Clerk Maxwell, the same guy of the electromagnetism, who used this technique to study the stability of this the steam machine with a Watt regulator. Okay, and the paper is very, very funny because sometimes he calls impossible numbers the imaginary numbers. Okay. Initially, this was not conceived. I mean, how can I have a number which is the square root of a negative number? Okay, so these numbers were considered impossible. And of course, Maxwell could do all the algebra with imaginary numbers, but here and there, sometimes he calls it imaginary, sometimes he calls it impossible. That's a funny thing of the article. The article is quite readable. I mean, usually ancient articles are very difficult to read because of the language, but this is quite readable. It's a funny thing. It was published, I think, 1865 or something like that. Okay, now what I would like to do is to solve a problem. I mean, I would like you to solve a problem. Okay, this is what I was looking for, but let's forget about it. So let's let's maybe later we can come and speak about HIV and so on. So suppose you know these animals, Marsupilami and Tasmanian monster. Did you know them?
Yeah, Tasmanian devil, I know.
Okay, but probably know the Tasmanian monster that really exists, which is not serves as inspiration for this one. These are characters from comics. You like comics, comic books?
Yeah, more or less. I used to, but
I like it very much. And you see Marsupilami. So we have these two animals, and the dynamics of these animals are like this. Okay. So X1 is Marsupilami and X2 is the Tasmanian monster. And we want to know how they evolve and to solve questions like, suppose that they were living in a, say, imagine an island. Tasmania is an island.
yeah.
And there are no other animals, but they became extinct. Okay. So the Minister of Ecology and Environment received a proposal to introduce a number of marsupilamis and monsters there. And someone said, okay, you are just wasting your money because you put there a few couples and they will also become extinct after a while. But some other guy said, no, no, they are going to multiply themselves. In terms of stability or instability, what does it mean in terms of the system of equations that model the interaction of them? Can you tell me? Whether they becoming extinct or whether they multiply, they grow, the populations grow.
Probably the number of, for instance, if the number of X2 is too small, so there is
No,
almost.
I'm not asking you to give me the answer, but in terms of our concepts, okay, the fact that you introduce a few, you have no numbers at all, and then you introduce a few people, a few elements of the species. Now they can again become extinct, or they can grow.
They can
And,
grow probably, yeah.
but this corresponds mathematically in terms of what?
So it's like a equilibrium.
The equilibrium would be 0, 0. No, actually, is 0, 0 an equilibrium in these equations?
No, I don't think
No.
so.
What is 0, 0? X1 equal to 0, X2 equal to 0. So
Then
what
it will be
happens?
zero, yeah, of course. In this case.
Because you have 0 times something, this is 0.
Yeah, it's a zero, yeah.
X2 equal to 0, this is 0. So 0, 0 is an equilibrium.
Zero.
Now, deciding whether they become extinct again or they grow means what in terms of our language of system theory? Is the equilibrium is what or what? So you have no elements at all, and you introduce a few ones. So you introduce a small perturbation.
If the equilibrium is stable, they will extinct again.
Okay,
and if
so
it isn't, they will grow.
so if it is unstable, they will grow. Okay, so it's the notion of stability. So how could you decide something about what is the approach here? Assuming that you have this model, what is the strategy to give the answer to the Minister of Ecological Affairs. Last class we had an example of war. Now we progressed a lot because we have ecological problems and marsupilami, which is quite nice. Even the monster is nice.
So we compute equilibrium points.
So in this case is 0, 0, and then I want to study the stability of the equilibrium point. How can I do it?
Are we assuming that it doesn't have another equilibrium point?
I'm just considering the 0, 0.
The 0, 0. Okay. So we can do the linearization. And then we have that matrix A, compute eigenvalues and eigenvectors, and study if it is stable or not.
And look at the sign of the real part. So that's one possibility. Now, then they said to the minister, okay, that's very nice. But probably they cannot coexist. I mean, one species will eventually grow, but then they go to 0, and the other predominates, survives. But other people say, no, they are going to live together and reach an equilibrium. How can I study that? Do I have an equilibrium in which they exist? Remember this, M1, sigma 1, alpha 1, M2, sigma 2, alpha 2, they are numbers, okay? Let's put numbers. Okay, and the numbers are, I don't have them here. The numbers are the M's are 1, the alphas are 0.1, and the sigmas are 1, okay? So everything is 1 apart from the sigmas. So these sigmas are, sorry, let me remember again. So the alphas are 0.5, the alphas are 0.5, and the M's and the sigmas are 1.
1, yeah.
So what type of analysis would I make to show that actually one of both species will grow together, and if there are some perturbation, they will return to this equilibrium. So what should I do?
So if the values of M, sigma, and alpha are equal for both.
So you can see my cursor?
Yes.
So if this part should be what? What are you are referring to this part between the brackets?
Yes.
And then what you do with this part?
It's equal to the one that we have between brackets in the second equation, right?
What is the condition that you are looking for?
Oh, no, sorry. No, it isn't.
What is the equilibrium that you are looking for? What is the thing? You are looking for an equilibrium. For an equilibrium, the derivative is 0. So the term between brackets should be what?
Should be 0. So
0, 0. This is equal to 0, and this defines, in geometrical terms, what does this define? This is a linear form in x1 and x2. So if you force it to be 0, then what is the relationship between x1 and x2 in geometrical terms?
must be equal.
A straight line.
Yeah, it's a straight line. Yeah.
And then you have here another straight line. And then
again 0. So
again 0, what does it mean again 0?
it's, they must be equal. So
Okay, equal to 0. So
yeah.
what you end up with what? With a system of algebraic equations, okay, that define what? An equilibrium point. Now, if you want to show that they can coexist, what will you do?
We study the stability of that point.
Again, in that
Yeah.
new point. So linearize, build the A matrix, compute the eigenvalues, look at the real part of the eigenvalues. That's the same. But now in a different point. Okay? Now, is there a situation, is there an equilibrium in which only one of the species exists and the other vanishes? What is the condition? Suppose that the first one vanishes. What does it mean?
Means like
X1 equal to 0.
0, yeah.
So look at the first derivative. What happens?
It's 0.
It's 0. Now, you are looking for a situation in which x2 is not 0. Is it possible? What are the values of x2 that make dx2 dt equal to 0?
X2 equal to 0.
Okay, but that I'm not interested because that corresponds to the situation neither marsupilamis nor monsters, or
the other term
this
0.
term equal to 0. Okay, and this term equal to 0 means x1 is 0. So what is the value of x2 that makes this 0?
M2 divided by sigma 2.
By sigma 2. So now, maybe it could happen that x1 does not survive, x1 is 0, and x2 survives. So you want to rule out this situation, this condition. So what would you prove? What would you look for? This again is an equilibrium point, and you don't want this to be asymptotically stable, because if it is asymptotically stable, probably you go there. Okay, so we want to show that it is unstable. Okay, let us write. We have 45 minutes. So stop share. So let's write the equations. We have x1 dot is equal to x1, and then we have 1. Okay, multiply these numbers by 1000 if you want, minus x1 minus 0.5 x2, and then you have x2 dot is equal to x2, 1 minus x2 minus 0.5 x1. Okay. Before we go on, is this reasonable in terms of model? What do you think? Can you justify this model in qualitative terms? Suppose that you just have x1, so you don't have x2. This term is not there. What does it mean? Is something that you know or not?
So it would be equal to x1 dot would be equal to x1 minus x1 square.
Yes, it is true, but if you just consider x1 times 1 minus x1 is something that you know, perhaps in a more familiar way. That equation is what? The famous logistic equation of growth with a limited value that we have studied and studied. Okay. Now,
Yeah.
you are growing. You are growing. Then you have a negative. What does this mean? This negative value of the population of x1. It means that you are competing with the ones of your same species by the resources. Now, this term here means that you are also competing with the same term, for the same resources, you are competing with the individuals from the other species. Now, what is the more intense competition? Is within the same species or with the other species?
Within the same.
Within the same, because here you have -1 and here you only have -0.5. Okay, actually, when you have this, you have an equilibrium point which is asymptotically stable that corresponds to both x1 and x2 different from 0. If you increase this number and make this number bigger than the coefficient of the interspecies, then the equilibrium point that corresponds to both being different from 0 is unstable. Okay? That's the principle of competitive exclusion. I mean, if two species compete for the same food, for the same resource, okay, they can only coexist if the competition within the same species is stronger than within the other species, than with the other species. Okay, so the interaction, in a sense, must be weaker than the competition in the same species. That's the principle of competitive exclusion. Okay. Okay, but let's forget about it. So let's think about equilibria. Equilibria. So one equilibrium is, let's call it point A.
Okay.
Is what?
0, 0.
So x1 equal to 0 and x2 equal to 0. So if you have x1 and x2, you have a point at 0, 0. That's point A. Now, then we have what? Let's say x1 equal to 0 and
x2 equal to,
or if you want to x2 equal to, write a full expression.
1 minus x2 equal to 0.
1 minus x2 minus 0.5 and 1 equal to 0. Okay, this is 0. So x2 equal to 1. You agree, Kaveh?
Yes.
Yeah.
Okay. So it's from making this term 0 and this other term on the second 0, you get x2 equal to 0. Equal to 1, sorry. So you have another point which is, say here, that this is point A, this is point B. Now, point C, point C. Tell me. Maybe by symmetry. So we have done this one with this one with that one. Now?
I'm sorry. The point B.
Point B?
Shouldn't
Oh,
it
yes,
be on
sure. You are
the...
absolutely sure.
Yeah.
Okay. So the point B is not here. The point B is there. B. I did this to see if you were attentive, if you were with attention. Good. What about C?
x2 equal to 0.
X2 equal to 0. And then, so x2 equal to 0. And
1 minus x1 minus 0.5, x2
so
equal to 0.
that one. Which means that x2 equal to 0, this term vanishes, 1 minus x1 equal to 0. This means that x1 equal to
1.
1. And now I have point C here. Now let's look at D. Do we have anything left?
Yes, when we say that the terms...
This term is equal to 0 and
That's
This one is 0.
And this is also equal to 0. So
Oh, yeah.
1 minus x1 minus 0.5 equal to 0, and 1 minus 0.5 x1 minus, this is x2 equal to 0. Okay. Now, how can I solve these equations? So I have, let me write them here, 1 minus x1 minus 0.5 x2, this is equal to 0. So what shall I do? I can multiply the second one by 2, so I get what? 2 minus x1 minus 2 x2 equal to 0. Good? Now I multiply everything by minus 1, so this becomes minus, this becomes plus, and this becomes plus, and then I add the equations. So this becomes minus 1, this becomes 0, and this becomes 1.5. x2 equal to 0. So x2 is 1 divided by 1.5. If you multiply by, okay, this is what This is approximately okay. So I remember the result. You can compute it with MATLAB or with the calculating machine in your phone or whatever you want. Okay. And what about x1? So you use this. Now you use x2 there. So you have 1 minus x1 minus 0.5 divided by 1.5 is 1 divided by 3. Okay, equal to 0. So x1 is equal to 2/3, which is the same as x2, no? Because if you multiply by 2, you get 2 divided by 3. And that's again 0.67. As percentagens não está lá dentro do frigorífico. Okay, so you have a point, an equilibrium point, which is 0.67 and 0.67. So we have a point 0.67, 0.67, something like here. Okay, that's point D. Okay. Now I want to linearize things, so I must compute the matrix of first derivatives. Let's compute it in general. So let's cancel out this stuff. This stuff is high school, huh? Solving linear algebraic equations. So we can cancel it out. And maybe I can cancel it since I have it there. So we'll have more space. Now remember that dx is, sorry, is df1 dx1 df1 dx2 df2 dx1 and df2 dx2. And let's clean this thing so that we have okay. So f1, let's write it here. F1 is what? Is x1 minus x1 squared minus 0.5 x1 x2. And f2 is x2 minus x2 squared minus 0.5 x1 x2. Okay, so compute these derivatives, please. So the f1 dx1. So the f1 is the x1 is what? So is you have three terms. The derivative of the first term
1.
1. Then the derivative of x1 squared
2x1.
and the derivative of the last term
0.5x2.
minus 0.5 x2. Don't forget the minus. Okay. Now df1 dx2. Sorry, df1 dx2. Yes. So the first term
0.
0. It does not depend on x2. The second term
0.
0, and the third term
minus 0.5x1.
minus 0.5 x1. Now df2 dx2. Sorry, dx1. Well, we could have completed the other, but let's go by order. So the derivative of the first one
0.
0. The second
0.
the third
minus 0.5x2.
and then we have df2 dx2. So the first term
It's 1.
1. The second
minus 2x2.
and the third
minus 0.5x1.
Okay. So this matrix is 1 minus 2x1 minus 0.5 x2, then minus 0.5 x1, then here minus 0.5 x2, and here what is 1 minus 2 x2 minus 0.5 x1. Okay. Now for point A, the origin, what does this reduces to?
Identity matrix.
So here we have 1 minus and everything is 0. So we have 1. Then this is 0. This one is 0. And this is 1. So if you compute the eigenvalues, what is the result? If you have a diagonal matrix, the eigenvalues are the elements of the diagonal. So you have two positive eigenvalues, 1 and 1. So what is the conclusion in terms of stability?
It is unstable.
It is unstable. Why? Where is it unstable?
So the real part is positive.
Yes.
And
what is the imaginary part?
It's 0.
0. No imaginary part. So what about oscillations? Do you have oscillations?
No.
No. So what is your evolution? Probably, if you start at equilibrium, stay at equilibrium, but let's suppose that you start here. Then you probably go like this. Start here, you go like this. Now, if you start here, at a point over the axis x1, where do you go? You should go away. But can you say something without the story of the eigenvalues by looking at the equations?
X2 is 0, so x2 dot is 0, and
so x2 dot
change.
is x2 is 0, so x1 dot is something, and x2 dot, you say that x2 dot is
0.
0 because x2 is 0. This is only valid over the x1 axis. And here you have what? You have x1, some x1, and then you have what? 1, and then what?
1 minus x1.
And that's it. Okay, so if you start here, where do you go? Remember that the abscissa of this point is 1.
Go to 0 again.
Towards 0? Towards 0? What happens? You have the product of two numbers. What is the sign of the first number, x1, if you are here? Is it positive or negative, x1, here? If you are here at this point, this is a very difficult question. Is x1 positive or negative?
Positive.
Positive, no? Okay, to the right. So this is positive. What about 1 minus x1 if you are here?
It's positive.
So x1 dot is what?
Positive.
And what happens to x1?
Increases.
Increases. So you are going this direction. Always over the imaginary axis, because x2 dot is 0. Now, if you start here, what happens? This is already away from the equilibrium, but we did not use any argument related to the equilibrium here. We just used the signs of the derivatives. So if you start here, what happens?
The same.
The same.
We'll go again. We'll go to.
So all these points, if you start there, you go there. What about if you start here, to the right of the equilibrium?
It will go to C again.
It won't.
Because why? Because here
x1 is positive, but 1 minus x1 now it's negative.
It's negative because x1 is bigger than 1. So this is negative, so you go in the opposite direction. It looks like that this is stable. Do you think this is stable?
No, it's not stable.
We don't know, but probably it's not. I mean, there is one possibility that it is not stable, because if you start here, maybe you can go away, okay? If you approach along a line, you approach actually this point, but if you introduce a number of x2, probably you go away. Let's see what happens. Now, in this case, you also have something like this. Okay, you can use the same arguments. And can you say that you have something like this at 45 degrees? Can we say that?
No, in this case, because the x2, it is, they must be equal. So
The equation's asymmetrical.
yeah.
Okay, the equation's asymmetrical. So you can write an equation. You know that since they are symmetrical, oh, well, let's be more, let's use another argument. Along this line at 45 degrees, what happens? You have for x1 dot is equal to x1 times what? Now, x2 is equal to x1. So this becomes 1 minus what?
1.5 x1.
1.5 x1. And the other becomes, using the same argument, x2, 1 minus 1.5 x2. And they are going here. So if x1 is now you can take the 1.5 from here, and this is the same as having x1 dot equals to 1.5 x1. Now 1 divided by 1.5 is 0.67 minus x1. Okay, so when you reach this point, it's an equilibrium corresponding to x2, x1 and x2 equal to 0.67. That's the equilibrium. For x1 and x2 smaller than 0.67, you are here, and the derivative is positive, so you go there. Okay? And if you come from over there, you have something like this. Okay? So we can do a lot of conclusions without solving the equation up to now. Okay? Now, I'm not going to end up this example today. We will continue. We will continue next week. But I put a challenge to you. So compute this is symmetric. So what appears here will appear there. So the 2 points for which it's important to compute the eigenvalues is D and C. Okay? C will be a saddle point, so a point in which you have two eigenvalues, real eigenvalues, one positive and one negative. So here you need also the eigenvectors. Okay? And sketch the eigenvectors and sketch locally, and then try to figure out what is the whole phase portrait. Actually, the solution, there is a simulation in the slide, but I would like you to make a presentation. So next class, I would like you to start the class by computing these eigenvalues and trying to sketch and making your own sketch. So Monday, that's the homework for the weekend. You should do it. Okay, you should complete the sketch. by computing the A matrix for point C, the A matrix for point D, computing the eigenvalues, you are going to see that actually this is a stable, asymptotically stable point, and for which there are no oscillations around it, so you are going to approach it. And then compute this. This you are going to see if it is a saddle point, compute the eigenvectors, and try to sketch things. Okay, it's a good way of learning. So next class you will give the initial part of the lecture. Okay.
Okay.
So both of you try to solve the problem, the whole problem, and then perhaps one speaks about one of the points and the other speaks about the other point, and both of you try to explain what is the, okay? Like a chorus. You can speak in chorus, no? Or like Huey, Louie, and you know what Huey, Louie, and Dewey, the nephews of Donald Duck. They speak. Each one says one part of the sentence. Okay, they are
Okay.
these three little ducks. One says one part of the sentence, the other says another, and the other says another. Okay. So, any question?
Yes.
No.
When we say that we are approaching an equilibrium point, it doesn't mean that it will touch that point, right?
It actually does not. It only touches the point at for t equal to infinity, because you would violate the unicity condition.
Okay. Yes.
Okay.
Mm-hmm.
Because otherwise you would have different solutions passing by the same point. So when I say that I go to here, I only go there. I really never reach there because it takes me an infinite amount of time to reach there.
Yes. Okay. Thank you.
More questions?
No.
Okay, so I will stop recording now.